And now we come to a new topic in vector spaces. Basis and dimension for the solution space of a homogeneous system of linear equations. There's a lot of technical words in there, and it's pretty hard to understand what this says, but as we go along, all these terms will become clear. I'm going to start out more theoretically, but we'll soon get into very practical examples of how to solve certain problems. And although the title says homogeneous, I'm actually going to start out by contrasting it with the non-homogeneous case. Remember, homogeneous with a system of equations means that it's all zeros on the right. A non-homogeneous means they're not all zeros. So this is an example of a non-homogeneous, two equations and three unknowns. Turns out this system has infinitely many solutions, and let's do the computation. I'll go through this fairly quickly. Won't bother using matrices. Let's just subtract twice the first row from the second row. That gives us this system, which is already in echelon form. The leading terms are the dependent constrained variables, and the other one, z, would be the free variable. So what we do is we let z equal a parameter. For example, let z equals t, and then we get y and x from substitution. We get y by plugging in z equals t here, and then we've got y and z here. And in short, this is what we get for z, y, and x. And here it is again in vector form. And of course there are infinitely many solutions because each value of t gives us a solution. Let's take two examples, say t equals 0 and t equals 1. Plugging in t equals 0 gives us this solution, call it u, and t equals 1 will give us this one, call it v. And we get a whole bunch of solutions that way. In mathematics we call that a set. So for each t we get a solution, and the set of solutions is a subset of R3. And the question is this set of solutions a subspace of R3? This might be the time to go and review the concept of subspace. Not every subset is a subspace. It has to satisfy three axioms, conditions. Now actually this set of S violates all three of the conditions, but you know, it's enough to say no to one of them, but let me go through all three. The first axiom or condition is that to be a subspace it should be closed under addition. In other words, if two things are in S, their sum should also be in S, but that's not the case. Let's take this u and v. U and v, each of them is a solution, so it's in S. But if I take u plus v, I get 5, 2, 1. And you can easily see that this does not satisfy the set of equations. It doesn't satisfy either one of the two equations. You should check that. So already S is not a subspace, but just for the practice, we'll continue with the other two axioms also. It's not closed under scalar multiplication, meaning we have, say, that u is a solution, but if I multiply it by a scalar, say 2, then that's not in S. It's not a solution because 2u is twice this is 440, and plug it in, you'll see it does not satisfy the system of equations. And lastly, the final death blow, if you wish, and usually this is the one I check first because it's easiest, is that the zero vector is not in the set. So that's one of the basic conditions for a subspace. I mean, the zero vector means x equals 0, y equals 0, z equals 0. Plug it into the SLE and you'll see it doesn't work. So what I'm concluding from all this, and why I looked at a non-homogeneous, is to show you that a set of solutions is not necessarily a vector subspace. That was for non-homogeneous, and in a moment we're going to contrast that with the behavior of homogeneous SLE. Okay, so this time let's consider the homogeneous system of linear equations. I took the same one as before, except that I put zeros on the right, so now it's homogeneous. And let's see what the difference is in the behavior. Like the previous one, this one also has infinitely many solutions. Going to do the same row operation, subtract twice the first row from the second row. And that gives us this. And once again, the x, which is the leading term here, and the y here are the dependent variables, and z is the free variable. Yeah, these two are, I think, called constrained. So we let z be parameter t again. And just like before, plug it in. And from here we get y, and then from z and from y we get x. And this is what it is. And I'll put it in vector form, like so. And just like before, let's take two example solutions by setting t equals 0 and then t equals 1. I forget what we did before, if it was 0 and 1 also. Anyway, we get u and v as these two vectors. And once again, we can consider not just these two, but all the solutions and call it S, and ask the same question. This time, do the solutions form a subspace of R3? And as you might expect, the reason I chose once non-homogeneous and once homogeneous is this time the answer is yes. And to prove it, we have to prove those three conditions or axioms. And I brought them in again to remind you. I think I may have rearranged the order. I like to put this one first, that the 0 vector belongs to the solution set, and if two belong, then so does their sum. That's called closure under addition and closure under scalar multiplication. As for the first one, the 0 vector is just 0, 0, 0. Just plug it in, see it in its solution. And I'm not going to prove these two. Let's just illustrate it with our particular u and v. Okay, u and v have just disappeared off screen, but yeah, check the sum. You'll see that this is it. Plug it into the original system, and you'll see that this is a solution. And scalar multiplication, again, just an example. Twice u is this, and this is also a solution. Again, leaving it to you to check. And so this time, in the homogeneous case, the solution set is a vector subspace. And since it's a vector subspace, which is also a vector space in its own right, now we can try and find a basis for it. At least not now, but later on we'll show how to do